Now we're going to go into detail about the different factors that can affect the range of a light, because the range that's listed in the book for how far it can be seen isn't necessarily true all the time. So there are four factors that will impact a light's actual effective range. The first two are the strength of the light, which is what's actually being described when you look into the book and it gives you its range. That's technically called its nominal range, just how bright the light actually is. That is working against the visibility conditions. So even if you have a strong light, if visibility is really poor, if there's thick fog, that will limit how far that light can actually reach. And then with those two on one side, on the other side, the range can be impacted both by the height of the light as well as the height of eye, which is just your height above the water, whether it's, at sea level or if you're standing on the bridge wing of a ship, whatever your actual height is. So geographic range is used to define this relationship here. This over here is technically, these two work together to determine luminous range, which we'll touch on next. But right now we're just going to talk about geographic range. So obviously, intuitively, it's pretty easy to understand that the higher up above the ground you are, or above sea level, the further you can see. We all know this to an extent. And to draw that out graphically, if that's the curvature of the Earth, if you're right here, you can see out pretty far in both directions, but once that line of sight hits the ground, which is technically your horizon, you cannot see any further, and everything over here is invisible to you. But if you were to be substantially taller, you could see much further that way and much further this way, so that your horizon eventually ends up being over here. You can see significantly more land or sea, but still this area over here is invisible to you. However, if we put these two together, let's say we add another little guy right here, they can see that far, and they're invisible to both this short tower here and this much higher one. But a substantially larger light like this, I won't even bother over there, it will be able to reach to there as well. The moment that this, let's just assume they're all lights, this light's maximum range hits the horizon at the same point as this one, now from this one's perspective, they can see some tower just barely peeking above the horizon way out in the distance. So even though it's many, many more miles away from the horizon, it's actually now visible, just because geometrically it's no longer being concealed by the curvature of the Earth. So if we interpret this now in the context of ships at sea, this could be a massive lighthouse, and this could be a ship. And the first moment where your two horizons meet is the furthest distance apart from one another that you could be, where you would still be able to see the light over here. If you were even a little bit further away, you would not reach, your horizon would not make contact with the light's horizon, and so the light would be invisible to you. But the moment you reach right there, it blinks into existence, just popping above the horizon. When you're out at sea, a good way to test this is you can actually, if you see a light show up, like you were watching it come into existence, you can duck your head really quickly, and that you'll see the light get concealed back under the horizon. Then you can lift up and you can see it again, then duck and you won't be able to see it. It's called bobbing the light. And that's just a good way of confirming that you're at this you're in this situation right here where you're as far away from the light as you possibly could be and still be able to see it. So the way you can calculate what the maximum distance you need to be where you can still actually see the light is from the geographic range table listed in at the beginning of the light list, just before the luminous range, and from there just before the actual lights themselves. And the way this is broken down is it just lists the height of any object and what its corresponding maximum horizon would be. We're assuming perfect visibility conditions. So it lists them, the height both in feet and meters. You can pretty much just ignore the meter section. And then it lists its corresponding ranges in nautical miles and statute miles. You can definitely ignore this. I can't imagine a situation, I think maybe on the Great Lakes, but otherwise this is totally unnecessary. So you're really just looking between feet and meters. And it goes all the way up to something being 1,000 feet high. If we're talking, skyscrapers. So you can see here, any object with a height of eye of 5 feet has a corresponding range, geographic range of 2.6 miles. Something with 40 feet has a corresponding range of 7.4 miles. But it's important to understand that we're only talking about this or this. If we're 5 feet high, this right here is 2.6 miles. If this is 40 feet high, that right there is, looks like 8.5 miles. That right there is 8.5 miles. So when you're calculating geographic range, you don't care about just one of these two. You care about both, the height of the light and your height of eye. And if you add the two together, that overall becomes the maximum range. So let's say we have a light that is 37 feet and we are 42 feet. Well, the geographic range table does not go into just ones here, so you're going to need to round that. It's fair to admit that this is all relatively approximate because we're working with pretty hazy concepts here. So we'll round this to 40 and we'll round this down also to 40. That's a bad example. We'll round this to 35 and we'll round this to 40. So you come here and you look, something with, zoom in, something with a height of eye of 35 feet has a range of 6.9 miles, and something with 40 is 7.4 miles. But I was right the first time, it's 7.4. So you would have 6.9 miles here and 7.4 miles there. Add the two together, you get 14.3. And that right there is the maximum geographic range. So anything more than 4.3 miles away from this light, and it is physically impossible to see it. There's no situation where it could be seen other than maybe like atmospheric refraction, like a really extreme case. But if we're just talking about the geometry of the Earth, it is not possible to see it until you are exactly 4.3 miles, when it will first appear on the horizon, and then as you get closer, you'll see it get higher and higher out of the water. If we take another example, let's go with something really big. So let's say this is 200 feet, and you are 70 feet. So you come back to the table. I move to the next section over, because that's where we get to the higher numbers. 70 feet gives us a range of 9.6 miles. 200 feet gives us a range of 19 miles. So we add them together, 9.6 and 19.0, get 28.6 total miles, being the furthest distance out that you could be able to see that light. So this altogether is your geographic range. And while I said it's kind of hazy just because we're rounding numbers into either 5s or 10s, this is also mathematically true to the point that two objects that have these characteristics will always be able to see each other at 28.6 miles given perfect visibility conditions.